All right, give me the reactants.
Sodium oxide.
Sodium oxide. And
Stir into water.
it's stirred into water, H2O.
I tried doing the inventory method.
Yes.
Do we supposed to do that, or do we have to write the full reaction?
Inventory method is the method used to write the complete reaction, but the complete reaction can be displayed in different ways. Do you guys prefer the microphone?
Yeah.
The complete reaction is different than what I call the complete equation. You know, the complete equation is, can you guys hear this? No. Maybe if I turn it on. Okay, how about now? Can you hear that? Okay. What I call the complete equation is when you have the complete formulas in the equation.
Yeah, I meant that.
But, oh, you meant the, okay. If you meant the complete equation, then you aren't going to do that for all the reactions. Because if you notice the acid-base method we talked about yesterday, you end up with a net ionic equation. And so for acid-base, Bronsted acid-base reaction, I expect only the net ionic equation. If you were to do the phosphoric acid one that we did, metathesis, then I'd expect the complete equation, the ionic equation, and the net ionic equation. All right. And so that depends on what type of reaction this is. If this is a metathesis reaction, then I would, yeah, do it. But can you look at this and see right off, is this a metathesis reaction or not a metathesis reaction?
No,
And how did you determine it's not a metathesis reaction?
because I saw Bronsted lowry acids and Bronsted lowry bases.
Well, yeah, that's what it is, but how did you rule this one out as being not a metathesis reaction? I mean, you're absolutely right. This is a Bronsted acid-base reaction.
And when I do the
What?
double replacement thing, I get weird products.
All right, sometimes water is used in double replacement, you know, because this is AB, but what is CD? You know, metathesis deals with ion. Unless if you have a weak base like the amines, then you could deal with molecular compounds too. But water is a molecular compound. Sometimes in metathesis, water is treated as the H ion and the OH minus anion. And so sometimes it goes A, B, C, D, like this. And so we would expect we'd expect something like this. You know, we'd have, but you know, this I don't really emphasize doing this because we don't have to do that if we just follow the methods that we're going to finish today. And so this I would rule this out as not being metathesis because you know, this is a molecular compound. Metathesis, you're looking for ion combinations, right? And so then we would inventory it and see, could this be a acid base? Automatically, when I see this is acid base because I look at sodium oxide. Sodium oxide contains oxide. Oxide is what is oxide? Oxide's not just a base, you know, well, it's a base. It's some kind of, it's a strong base. And it's not just a strong base because sodium hydroxide is a strong base. It's a powerful base. You know, oxides are very powerful base. But you think, okay, if oxides are powerful bases, then rust must be a powerful base, right? Well, rust is not a powerful base. Why is rust not a powerful base? Well, you know, you say, well, didn't you just say oxides are a powerful base? Yes, I did. I said oxides are a powerful base, just like hydroxides. But when I say hydroxides are a powerful base, I don't mean every single hydroxide. I mean the soluble hydroxides, just as I mean the soluble oxides are going to be powerful bases, and group 1 oxides are soluble, right? And so this, when I look at sodium oxide, I look at a powerful base, and this is why I said carefully stirred, because if you stir it, you know, if you just dump it in, it's just gonna go everywhere, you know. And so you got to be careful with this stuff, sodium oxide. What were we doing? Oh, I think we were using sodium oxide. There's a, I was doing this nursing chemistry class in Santa Barbara, and we were using, I think we were using sodium oxide. And these are nursing students. This is their first chemistry class, so I don't know why they were using such a powerful base in this class, but they were supposed to mix it with water. And the reaction started to go out of control, and the student started to panic. At this time, I was being evaluated. The dean was sitting there watching. And so we had a little emergency situation. But, you know, normally what I do, you know, if a reaction starts to go out of control, what do you do? Well, one is you just, like, if there's ever a fire in here, you know what you're supposed to do? Just exit, get out. That's what you're, just leave it. Because this room is supposed to be able to contain fires. And so the fire will just be isolated. And so you're not supposed to risk your health trying to put out the fire. If it's a small fire, just smother it, you know. Well, this, you know, normally what you do is, and this is what a lot of synthetic people do, if the reactants aren't water sensitive, you have an ice bath near you. Because of kinetics. The way kinetics works, it's non-linear. So if you cool it down, the reaction slows dramatically, usually. And so ice bath usually does it. Ice bath will. And so we didn't have an ice bath, so I just started flushing it with cold water. Unfortunately, that was enough to calm the reaction down. But anyway, this it wasn't going to explode or anything, but it, you know, it was just getting pretty violent. Okay, sodium oxide, solid, and water. So what we do is we inventory it. Sodium oxide, is that soluble? Yes, sodium salts are soluble. Is it a strong electrolyte? Yes. So if you mix sodium oxide and water, this is what's going to happen. If this were an insoluble salt, I'd leave these as solid state. But we're going to get sodium ions in solution, we're going to get oxide ions in solution, and we have water, right? And so you inventory it. And then what did you do after you inventoried it? June? What do you do after you inventory it? Yeah. Determine acids or bases. Strongest, well, sodium ions are neutral. Oxide is water or base. Yeah, and so, you know, we only have one choice here, oxide and water. So oxide plus water yields what? Well, this one picks up, so we're going to end up with hydroxide. This one's going to lose, so we end up with hydroxide. Hydroxide and hydroxide. But this is the funny thing. The funny thing is this. This is the base going forward. This is the acid going forward. What is the base? What is the acid going backwards? Yeah, one of each. Actually, if this oxide picks up a hydrogen, then this is the base, and so this is going to be the acid. So one of the hydroxides is the acid. The other hydroxide is the base. Uh-huh.
But wouldn't it produce two hydroxides?
It did. It's 1 and 2. So for every mole of oxide, we produce 2 moles of hydroxide. But the reason I wrote them separately rather than combining them is because one hydroxide, yes, they have different roles in the reaction. So it's best to separate them. This way, when we go to the chart, we can compare. You know, what's a stronger base, oxide or hydroxide? This one you should have memorized. You guys memorize the 7 strong acids, right? You should know oxide, sulfide, amide. And so those are stronger than hydroxide. As far as acids go, what's a better acid, water or hydroxide? For sure, water. I mean, no, that's much stronger than hydroxide as an acid. And you can determine that structurally too, because the simple structural arguments is water's neutral. So if it loses an H+, it's going to form a negative charge, but hydroxide already has a negative charge. So if this loses an H+, it's going to gain another negative charge. So it's going to be -2, which makes it even less stable. So we have driving force here, and then we get the thing. Strong bases are strong electrolytes. Strong electrolytes hydrolyze water completely. When I look at sodium oxide, I see two things. I see soluble salt. Soluble salts ionize completely. That is, they break apart into ions. So that's what we did here. And then I see, oh, this one is the strong base. Oxide. All right, other questions?
Number 3 on the homework, it's iron 3 sulfate solution and ammonia solution together.
Iron 3 sulfate and ammonia. Okay. Iron 3 sulfate and ammonia is very similar to magnesium nitrate and ammonia. And so, let me give you that hint and then see, it's just like the problem we did yesterday with magnesium nitrate. Almost, a little bit more difficult. But see if you can kind of model it the same, and if you get stuck, we can go through it. But first check that, and give it one more go, and then I'll cover it. But when I see a salt, like a metal, like iron, metal ion salt, then one of the chemical properties of ammonia is it participates in metathesis reactions as a precipitating agent, hydroxide precipitating agent. And so when I see ammonia and a metal salt mixture, I always think of precipitation of hydroxides, right? So that's one of the chemical properties. There are other chemical properties of ammonia, and so ammonia might not always result in a precipitate with metal salt solutions. We're going to see that today. Yes?
Ammonia also has a tendency to form complex ions.
Yes. Ammonia has a tendency to form complex ions in what are called Lewis acid-base reactions. And so those do not result in a precipitate. And those are something we're going to talk about quite a lot in chapter 24.
Like the copper, like when you add excess ammonia, the solution turns from light blue to like a dark blue.
Exactly. Yeah, that's a Lewis acid-base reaction. We're going to talk about those today. So aqueous ammonia in metathesis reaction. So if you have AB, that is an ionic compound plus aqueous ammonia, think a hydroxide precipitate. You think of ammonia as being ammonium ions and hydroxide ions. And so looking at that problem, I would predict we're going to get iron 3 hydroxide and something else, right? Ammonium sulfate. But write it like I did, ammonia and water, not ammonium hydroxide. All right, other questions? Now, when we're dealing with Lewis acid-base reactions, you know, what we just did was a Bronsted. So Bronsted's kind of, you just look at the chart or you can just figure it out from what you already know. But Lewis is a bit more difficult because, you know, you look at something like CO2. Let me try to analyze this. You know, what we did was we did the oxidation states. Oxidation states I like to write in parentheses. A formal charge I like to write with circles. 0, 0. But the reality is it's not 100% ionic in its oxidation state. It's not 100% covalent. It's somewhere between the two extremes. In fact, we call these bonds polar covalent bonds to indicate that they're somewhere between covalent and ionic, right? And so that, in that case, we end up with this, which is fairly closer to reality. It's some partial negative charge, partial positive charge, and partial negative charge. Again, those partial charges we can determine from quantum mechanics, right? Good. And so here, we say, okay, this is negative charge density with a lone pair. That's going to be a base site. A base site's just an atom that has some reactivity. This carbon is a, you know, we already do this? Acid. This is going to be a base site. So carbon dioxide can react either way, right? It can react as a base or an acid. How about water? So plus water.
Wait, why is the oxidation state -2?
For oxygen?
Yeah, like how do you determine it from the Lewis structure?
How do you determine oxidation state from the Lewis structure?
Yes.
Okay. The way we determine it is by just dividing up the electrons. And so we can do that. We can do that over here. Determining oxidation states from Lewis structure is very simple. All we're doing is counting the electrons. You know, one bond is 2 electrons, and the lone pair is 2 electrons. So we're just counting the electrons. So if we look at CO2, we're looking at 2 opposite extremes, ionic bonds and covalent bonds. In an ionic bond, we're going to form ions. When we form ions, who takes the electrons? One species takes all the electrons, the other species loses electrons. So we form an anion, we form a cation. Which species takes electrons is the more electronegative species. And so when we do oxidation states, we assume that the more electronegative species is going to take all the electrons. But when I say take all the electrons, this oxygen's not going to take the electrons from this way over here. It's going to just take the, well, right now, we can think of this as being like a tug of war for electrons. They're being shared, but each one's pulling on the electrons. And so if you're not familiar with this, all I do when I do this is oxygen versus carbon. Which one's more electronegative?
Oxygen.
Oxygen. So oxygen takes all the electrons. If oxygen takes electrons, all of them, how many electrons does oxygen end up with? 2, 4, 6, 8.
8.
How many electrons does oxygen normally have? Valence 6. So it has 2 extra electrons. 2 extra electrons means 2 extra negative charges, which means -2.
Okay, you got it.
Got it? Okay. The other way, well, let me just finish it. Unless, does everybody get it already? Or? Yeah? The other way is we just split it. You know, if the bonding's covalent, then it's not winner take all. It's 50-50 sharing. And so the count is different, right? Count is going to be 2, 4, 6. Formal charge is 0 because broke even. Okay. All right. We can do the same thing for water. When you look at water, you know, normally we just say, okay, this is delta minus, this is delta plus, this is delta plus, right? And so here, this oxygen would be a base. And the hydrogens can accept a lone pair as long as it kicks out a lone, or a bonding pair. And so these hydrogens will be acidic. And so water can go either way. And so what that means is we have two possible reactions here. The two possible reactions is this. And in Lewis acid base, we talk about attack, this attacks that. But when we talk about attack, we always refer to it in the same way. It's always the base attacks the acid. The base is going to attack the acid because the base has a lone pair that's going to. The acid has, it's just an electron pair acceptor. And so when we think about these types of reactions, base attacks acid, which is different. Because in Bronsted, we think of protons being transferred. Well, how do they get transferred? Well, the base has to attack that proton. You think a water molecule is just going to give up a proton? No, a base has to come in and pluck that off. Now, we have two things that can happen. This base can attack this hydrogen, or this base can attack the carbon. And so those are the two possibilities here. So let's look at this here. Let's go with this base. And which way do you do it? Well, you do both, right? You just try all the possible, because in chemical reactions, what happens? You guys know about the kinetic molecular theory, right, from gases. You have a lot of collisions. These collisions can result in reactions. And these collisions, are going to be somewhat random. And so both of these are going to happen. It's just, will both of them lead to a reasonable product? And so what we're going to have here is, let's try this one. This is going to be route 1 here. This lone pair is over here. This is positive charge density. That's negative charge density. They're going to attract, right? Did we already do the oxidation states and formal charges in water? The formal charge is all 0. The oxidation state is +1, -2, +1. Water. But that is going to result in something. If those electrons get donated to the carbon, then carbon already has 8 electrons in its octet. When we count octets, we're counting the total number surrounding. An additional 2 electrons in its octet will give it 10 electrons. Can carbon have an expanded octet? No. Carbon cannot have an expanded octet. And so there's too many electrons. But what can happen is the pp pi bonding electrons can get kicked out onto the oxygen. And so we're going to use valence bond theory initially to describe these because it's easiest. This is, what's the hybridization of this oxygen? Is it sp2? So we got sp2 sigma, and a pp pi. And so these electrons come in, pp pi breaks, these electrons go to this oxygen there. And so the resulting structure is going to look like this. And so what was once an sp2 carbon is now, sp2 oxygen is now a, what's this? Let me back up. I need to back up because in my Chem 1A, I had everybody hybridize all the atoms, including the terminal atoms. Now what Petrucci does is he doesn't have you hybridize, right? The terminal atoms. So what did you guys do? Did you hybridize? How many of you did not hybridize the terminal atoms? You left them unhybridized. Okay. Well, for our discussion, because just like typically things aren't 100, there are 100% covalent, and there are 100% ionic things, right? But, and there are sp2 and sp3, but there are, the bond angles. Sometimes you get bond angles that aren't perfectly 109.5 or 120. Let's say the bond angle is 105. If the bond angle is 105, is that still perfectly sp3 hybridized? It turns out no, because if the bond angle is 105, that means the orbital hybridization has more p character, because the more p character there is in the hybrids, the closer it should be to 90 degrees, because 90 degrees is what you'd expect for p unhybridized, right? And so the level of hybridization varies. So rather than calling it sp2, sp3, sometimes we say percent p character or percent s character, because it's variable. It's not at these fixed numbers, but it can vary depending on the angles of the bond. You know what I mean? In certain sense. And so, this is all a result of valence bond theory. In MO theory, we do away with all this, and we have these MOs that take care of this stuff. But anyway, I like to hybridize this. So this is 4 groups. So this will be sp3. This was sp2. We went from sp2 to sp3. Everything else, this one's still sp3. This carbon went from sp to sp2. No, that's not sp. Is that sp2? Yeah, that's right. It's sp2. Well, ignoring all the hybridizations, how does this structure look to you? Does this structure look good? Does everything have an octet? Has octets been satisfied in this? Yeah. So everything has an octet, it should be good. Is it good? Everything has an octet, therefore it's good. No, it's not good, because whenever we look at a Lewis structure, we always have to determine the formal charge. And so the formal charges, what are the formal charges here? All the others are 0. Usually with formal charge, we only write the non-zero formal charges. So plus and minus. Does that look like a good formal charge distribution to you? No. No, basically one oxygen has lost an electron, another oxygen has gained an electron. And so, in other words, if you one way to visualize this, although this is not 100% accurate, but if there was a tug of war between 2 oxygens, then one oxygen would strip the other of its electron. Does that make sense? Because the tug of war is usually dictated by electronegativity. And so if we think about the electronegativity of oxygen, is that the 2 oxygens should be equal. They both have a 3.5 electronegativity, right? And so this doesn't make sense. This is very unstable, right? Having something like this. Now the electronegativities are way oversimplified, because you guys learned the Pauling's electronegativity, right? With fluorine it's 4.0, the others are down to 0.7 or so. Do you know what the range of electronegativities are? Tell me what the maximum electronegativity is and the minimum on the Pauling's table. Or do you just remember a jumble of numbers? You see, this is the difference. When people ask me, do they need to memorize them? No, you don't need to memorize them, but at least you should do is memorize the extremes so you know what the range is. You know, is there if I said true or false, there are atoms with an electronegativity of 0.01. Well, this is a trick question, because you only learn the Pauling's table. And the Pauling's table, no, it would be false. But Pauling's table is not comprehensive. Because what also changes is what kind of bonding arrangement there is. And so if you were to Google this, and look up more advanced electronegativity tables, what you'd see is, you'd see tables based on how many bonds it has and other factors which will influence how many lone pairs, this type of stuff. Those electronegatives do change. But if we assume these two have the exact same electronegativity, which they don't, but if we did 3.5 and 3.5, this is impossible, you know, because they're equal. And so how can one pull an electron from the other? It would be a tie, right? And so the end result is this doesn't look so stable. One oxygen has a negative charge, the other oxygen has a positive charge. Creates a voltage. Voltage requires work and energy to do that. You know, if you were to make a voltage, is that free? You know, let's say I have a dead battery. Can you make a voltage for me? I want it back to 1.5 volts. Is that going to be free, or is that going to cost me energy? It's going to cost you energy. When you create a voltage like this, it's going to cost you energy. And voltage is, you got a positive and a negative, right? So this looks not so stable. But if you look at this bond, what kind of bond is that? Tell me, in valence bond theory, what type of bond is that? It's a covalent bond. Be more descriptive. It's a sigma bond. Be more descriptive. Remember we did this. It's a blank, blank sigma bond. Yeah, it's an sp2, sp3 sigma bond. And so if you look at the orbitals, if you have an sp2 and sp3, if you were to rotate the sp3, would that upset the bond? No. Because you just got a lobe here for the sp3, you got a lobe here for the sp2. So what we say is, around sigma bonds, single bonds, actually it's just single bonds, there's free rotation. Whereas here, well, how would you describe this bond for me? It's a double bond, which consists of one sigma and one pi bond. Tell me the sigma bond here. This would be an sp2 on carbon to a oxygen. Now, it depends. If you did this without hybridizing the oxygen, you'd say it's an sp2p sigma, right? And what would the pi bond be? A pp pi bond. Now, is there free rotation? If I were to rotate this oxygen, the sp2 sigma wouldn't break. That would be no problem. But what would happen to the pp pi bond? The pp pi bond would have to break. And so what we say is, you know, with double and triple bonds, there's no free rotation. Right? And so there's something called conformations. Right now, this hydrogen's pointed this way. This is not very accurate because we know this is not a T shape. What is the shape on this? Trigonal planar. And what is the shape on this, the geometry? Well, it's a tetrahedral electron pair geometry, but the molecular geometry is trigonal pyramidal. And so anyway, what we're going to do is there's free rotation. These are called conformations. You know, where the positions of these atoms are is a conformation. And different conformations yield different energies. And so this hydrogen is delta plus. If this hydrogen is delta plus, it probably want to be more associated with this than this. But you know something. One thing is this negative charge. Can this negative charge, have you heard this term, right? Delocalize. Is it possible to delocalize that negative charge a little bit? Tell me how we could delocalize that negative charge to help stabilize it, this structure.
Split it between the two bottom.
Yeah, split between, how can we split it between the two bottom oxygens? Well, we dash about, what we do is we just rearrange the electrons, right? So if these electrons pop down here and we pop these pi electrons out, then we come up with what's called a, what do you call that?
Hybrid.
Well, the hybrid's a result of combining all the resonance forms. And so we call it a resonance form. Resonance form for this, right? We could do different things, but you know, we got to use structure for Chem 1B, of course. And so this is a little bit of review. I don't want to review too much though. It's take too much time. But people always ask me, what should you review for Chem 1A? If this stuff isn't easy for you, then you should review this for sure. You know? This should be pretty straightforward. So that's going to help stabilize that negative charge. And when it stabilizes it, then we end up with the resonance hybrid. The resonance hybrid would have what formal charge on each oxygen? -1/2. Good. And that would lower the potential difference, right? Or help spread things out and help stabilize this. But still, it's not going to be all that stable, is it? Because we still got that formal charge there. And so it's still looking to react. And so in reality, what I'm going to do is I'm going to change the conformation of this, but in reality, it doesn't make any difference at all because, you know, what we're going to have is something called an intramolecular proton transfer. And so I did this in Chem 1A, this one. And if you look back at the notes, I didn't talk about this at all because I didn't want to make things more complicated than they had to be. But what I did was I just switched the conformation. I just rotated this so it's close to this one with the negative charge, right? But in reality, I didn't need to rotate it because it was going to react with either just fine because both of them are the same. Both oxygens are exactly the same, right? But you know, this is just helpful sometimes just to look at one, because if we did have an oxygen with negative charge versus an oxygen with no charge, oxygen with negative charge is going to be much more reactive, right? And anyway, there's going to be a reaction here, possibly. There's possibly going to be a reaction because we got this negative charge here. This negative charge here is going to be attracted to this delta plus here. And so this negative charge you can think of as base, like hydroxide, right? What does it see here? Well, it sees something like this. Because now think about this. If this oxygen has a positive charge, that oxygen is lacking electron density. This oxygen is lacking electron density. It's going to suck in as much electron density as possible. So compared to water, let's compare the size, the magnitude. Does this oxygen have any formal charge? No. What's the oxidation state on this oxygen? -2. What's the oxidation state on this oxygen? -2. The oxidation state doesn't tell us anything. The difference is the formal charge. 0 formal charge, positive formal charge. Are these two oxygens going to have the same electronegativity? An oxygen with a 0 charge versus an oxygen with a positive charge. Will they both have the same pull for electron density? No, not at all. And so an oxygen with a 0 charge, we typically think of as having an electronegativity of 3.5. An oxygen with a plus charge is going to have an electronegativity greater than 3.5 or less than 3.5? Greater. And so this oxygen is going to be highly electronegative, which means it's going to suck more electron density from the hydrogen, which means the hydrogen is going to be even more positive, right? And so this is ripe for reaction here. Do you see the negative and positive? And so, well, the other thing is, you know, even there's rotation, but what other types of kinetic energy are there? There's rotation, there's 3 types of kinetic energy. Rotation, vibrations, and rotation, vibration, and this is back in chapter 6. You know those are quantized. Did you know rotational energies are also quantized? Vibrational energies are quantized. Translational energies, are translational energies quantized? No, translational energies continue. Continuous, as long as there's nothing holding them. Like electron is not, a free electron is continuous. A confined electron in a box or an atom is quantized. Well, there's vibrations. Now, the last one was translational, but there's vibrations. And so this oxygen vibrates. So what orbital is this lone pair in? This is why I like to hybridize. Just hybridize the terminal atoms. Otherwise, you can't answer that question easily. Is that, I don't know, 2s maybe, or 2p, right? But if this were hybridized, then it's easy. It's sp3. This is an sp3 orbital. This sp3 orbital gets pushed into this. This is an sp3 bond. So it gets pushed into the s orbital, and hydrogen kicks out the sp3 electrons here. And so what happens is these electrons get pushed into the hydrogen's s, which is going to kick these sp3s onto the oxygen. This is called an inter or intramolecular proton transfer. This is called an intramolecular proton transfer. Intermolecular is what we just did with sodium oxide. It's between two different. But we can have proton transfer here because here's our base, here's our acid, right? This is the base side, this is the acid side. This is going to be like a Bronsted or it could be a Lewis, either way. This is an acid-base reaction. It just so happens it's in the same molecule, but sometimes you got these gigantic molecules that can easily do. Well, anyway, this intramolecular proton transfer is going to help stabilize things because it's giving some of that negative charge density back to this oxygen. And so when that happens, and again, this is more complex. I'm ignoring the hybrid. Really, the hybrid is the most accurate, right? And oftentimes we just do that. We'll just pick one of the resonance forms and have that react because dealing with the hybrids is a hassle. That makes sense? But you should know, obviously you should know that, oh yeah, we're doing that. Whereas the hybrid should be. The hybrid should be, and so it's hard. Well, anyway, that's what we do when we do Lewis. We'll just pick one of the resonance forms and react it. Not worry about the hybrid. We end up with this. Now, the nice thing about this is, what are the formal charges here? All zero. And the oxidation states are all the same. In an acid-base reaction, oxidation states don't change. And so this structure looks good. Do you know what the name of this is called?
Carbonic.
This is carbonic acid. Now, why the heck, carbonic acid looks very stable to me. This should be fine, right? But, thermodynamics tells us that CO2 in water is more stable than carbonic acid. And so what we could do in thermodynamics is we could look at maybe the bond energies. Do you guys, I didn't do this that much, but in Chem 1A, you could look at the bond energies. Maybe the sum total of bond energies of the reactant is greater than the sum total of bond energies of the product. And that means, then the reactants are favored. We already know that this side's more thermodynamically stable because you memorized. You memorized carbonic acid decomposes spontaneously to CO2 and water. But even so, even so, an easy way to lower the pH. I didn't bring a straw, but is let's say you have a light pink color, and the light pink color disappears in your acid-base titration. You didn't do anything. You didn't touch it at all. Why did the light pink color disappear? The phenolphthalein go colorless? Because of CO2 and air. CO2 and air. If you want the light pink color to disappear immediately, take a straw and blow in it. And the light pink color is gone right away, because you're going to just acidify the water, forcing more carbonic acid formation. Okay. Anyway, in Chem 1A, and I didn't emphasize this in my Chem 1A class, but in Chem 1A you learned that non-metal oxides, like CO2, are acidic. That's in the periodic trends after quantum chapter. Non-metal oxides are acidic. Metal oxides are?
Basic.
What about semi-metal oxides? Non-metal oxides, acidic. Metal oxides are basic. Semi-metal oxides are? In between. What's in between? Amphoteric. Non-metal oxides are amphoteric. They react either way. They're in between. So what happens if it went the other route? Remember, carbon dioxide didn't have to react as an acid. In this example, carbon dioxide reacted as the acid, right? What if carbon dioxide reacted as the base? It could, right? And so what if carbon dioxide reacted as the base? And water reacted as the acid. Well, okay, if carbon dioxide reacted, this would be scenario 2. So this attacks this, which is going to knock these out. And so this sp2 goes into the S, which kicks out the sp3. This is sp3 sigma bond. Results. So it looks like we got some hydroxide here, and this. This oxygen will have a positive formal charge. Okay, now we have this weird cation here, but looking at this, is there a way we could stabilize that positive charge, get rid of it, or delocalize it some way?
How about try rearranging the electrons?
We could try rearranging electrons. In fact, maybe we'll kick these pi electrons out here. Right? But if we kick these pi electrons out onto the oxygen, then that gives carbon less than an octet. Unless maybe we'll drop some electrons there. So in order to maintain the octet. And so let's see what we end up with here.
I don't know what molecule is that.
I'm sorry?
I don't know what molecule is that. It's so weird.
Well, what's wrong with it? Why is it weird?
I mean, no, just looking at it.
Yeah, so maybe, well, what's weird about it? Is the octet violated? No? What's weird about it?
The formal charges on the oxygen.
Yeah. All right, what formal charge? Where's
The electrons.
Is what? What's the formal charge here?
Because because oxygen doesn't is not supposed to have a triple bond. So
Why not? Why not? The thing in science is this. If you say something like that, somebody's going to ask you, why not? Well, because my teacher, my fourth grade teacher told me so. You know, unfortunately, they're going to hold you accountable. They aren't going to look for your fourth grade science teacher. I remember, no, it was seventh grade. I remember in seventh grade science, I was told about atoms. You know, I never questioned it. I always believed in atoms, because my seventh grade science teacher told me. And so all through this time, I believed in atoms, until somebody asked me, well, what's your proof? You know? And so this is why I always ask my Chem 1A students, you know, why do you believe in atoms? And if so, then prove it. And I'm always looking, because my seventh grade science teacher told me so, as the proof, you know. Nobody's ever said that. I was going to say something like that, maybe. And so, why can't oxygen have a triple bond? Who told you that?
my teacher did.
Your teacher told you that? Oxygen will never have a triple bond? And what was the reasoning for that? This is, you know, I'm not trying to be nasty or mean, but in science, sometimes people come off as being nasty or mean because they start questioning you, and then they start, you know, probing and saying, and they say, well, why you, you know. But it's just the way science is. They're just being curious. It's just very curious. That's all. And so most scientists are actually very nice people, although they come off as very
Short.
yeah. And so if you said that, let's say at a meeting or a talk or something, and oxygen doesn't form triple bonds, somebody's going to nail you on that. Somebody's going to come up to you and say, I don't believe that. You know, tell me your reasoning why. Well, I'm going to say oxygen is perfectly fine with a triple bond, right?
Oh yeah.
And so what's wrong with this structure? Well, you know, triple bond, this is sp hybridized, so we just got two pp pi bonds. sp sigma bond. Nothing wrong with that. Could be, then there are other arguments that you can come up with. For example, do you know oxygen single bonds are very unstable? Oxygen single bonds are unstable. Yeah. Do you know why oxygen single bonds are unstable?
I don't know. I don't know.
These are called peroxide bonds. The reason they say is because the two nuclei get too close to each other, so the repulsions become great, and the bond energy is very low. The bond energy on this is like in the 100 kilojoule. I think it's about 150 or something. It's like iodine bond. Iodine bond's like 100 kilojoules per mole, very weak. You know, visible light can break it. Okay. Visible light can break this bond too. So you might argue, well, I think it's unstable because, you know, maybe triple bonds are very short. Maybe there's going to be too much nuclear, you know, positive repulsion in this. That could be an argument potentially. I don't know. You know, maybe they just say, you know, you haven't seen any oxygen triple bonds. Therefore, that's why you believe it.
Yeah.
It's not the case. Or oxygen triple bonds. We'll stop soon. Right. But it's the formal charge, you know. The argument against this structure is not necessarily the triple bond, but the, yeah, we can't get rid of that. And the first one is going to be on oxygen. We can't bring it to carbon. You know, maybe carbon might be better accommodating. So this is going to be very reactive, right? And so this is unstable. Maybe we could do some kind of intramolecular, if we did an intramolecular proton transfer, this can't reach, right? This is bent, right? But this can't reach over there. You know, it would have to have some amazing vibration because this is linear right here. And even if we did a proton transfer, we would end up with the same thing. Right? And so the only thing is we could have an intermolecular proton transfer. In other words, in that space, and if we did that, we end up back at this. And so this is a dead end. If this collision were to occur and these products form, they're unstable, they're going to react, they're going to come back this way. Right? And so this is why CO2 is known as an acid because, well, maybe it could react as a base. Depends on what you reacted with.
So there's only one pathway for this.
For this particular reaction, there's only one pathway because if we did the other one, we end up at a dead end. And we end up back where we started. All right, let's stop. We're going to take a break here, and then we'll start again in 10 minutes or so.